now let's talk. We talked about binaural cues before, which are cues that require both of your ears. Now we need to talk about monaural cues, which are cues that only require one ear. We do have the ability to use the sounds bouncing into one ear to compute certain things about the sound, the location where the sound is coming from. The physics of the monaural cues involve the pinna and your head, right? The way the sound bounces around your head, as well as the pinna of your ear. The pinna of your ear is this right here, the outside part of your ear. That's the pinna. Um, and one of the ways that we have done research on how sounds bounce around inside of the pinna is we've placed tiny little microphones inside the ear so that these microphones can hear or pick up the same vibrations, the same sound frequencies that your eardrum picks up. So, in other words, we're able to record with high precision the exact same types of sounds that hit your eardrum as they bounce around inside your ear. Um, the sound, the frequencies. One of the things that we measure is the intensity of the frequencies. So high frequencies, low frequencies, we measure how loud they are or how intense they are as they go into the ear canal. And we look across the entire spectrum of frequencies. So, for example, we can put a special microphone into the ear. So here's a pinna, right, of somebody's ear. And we can go ahead and measure the sounds at different elevations, for example. Um, so we can measure a sound that's coming from 15 degrees below you and 15 degrees above you. And what you can see here is a graph. The x-axis of the graph is frequency, and the y-axis of the graph is decibels, meaning how the intensity of the sound. And what you can see here is that sounds that are starting at about 400 kilohertz or 4,000 cycles, when they come at us from either the 15 degrees elevated or 15 degrees below us, are much higher in intensity than sounds as we get higher and higher. Higher and higher frequency. So the lower sounds going from like 4,000 till about maybe, oh, I don't know, 6,000 or so, are higher frequency, a little bit higher frequency than those sounds going from about 8,000 on to 9,000. And the reason this is important is because right around here is where voice is. Our voices are generally around in this range. So what you can tell here is that our ears are tuned specifically for hearing voices. And of course, we hear voices a little bit better. We can hear these sounds a little bit better. They're more intense if they're coming from slightly above than they are from slightly below, as you can see in this graph. Now, one of the things about monaural cues for sound localization is that they are very useful for detecting elevation, where sounds are coming from, whether they're coming from above you, at your same level, or below you. Look at this graph here again. Notice that with one ear, you can tell if a sound is coming from a 15-degree elevation or a minus 15-degree elevation. That's because the intensity of the sound hits your ear differently based on whether it's coming from below you or whether it's coming from above you. We can use this information to calculate where sound is coming from in elevation wise. Now, we cannot use our binaural cues, our ILD and our ITD, to judge elevation. It's not very good for that at all. And the way we know this is by doing studies where we put a mold inside a little object inside of people's ears that changes the shape of the pinna. And when we change the shape of the pinna, we change the way the sound bounces around in the pinna and then goes into the ear. And we're able to alter the perception of elevation based on how we change the shape of the pinna. So right after I put these moles into your ear, um, the I can make your elevation judgment go away. I can make it sound like all sounds are coming from right at ear level, even if they're coming from up above, right? And it will not affect the azimuth, whether it's coming from left or right. It only affects elevation judges. Um, However, if I leave those moles in for 19 days and keep testing you again and again and again, something really interesting happens. Your ability to judge elevation comes back. In other words, you've adapted to the goofiness of your ears, you've adapted to how they've changed, and you're now able to judge elevation again. If I remove the moles after 19 days, you're still okay because you go back to remembering how you were able to judge elevation before. This suggests, since the fact that we're able to judge elevation when our pinnas are changed versus um, we're still able to judge even when the moles are removed, suggests that there may be different sets of neurons that are using the different cues. So there may be a set of neurons that uses that analyzes the cues coming from below. There may be another set of neurons that's analyzing the cues that's coming from above. If it was all one set of neurons, if one set of neurons was responsible for analyzing both the above and below sounds, you wouldn't expect people to perform well after we took away the moles because it would take those neurons a while to readapt, right? You would think, oh, they have to readapt. The mold came out. Now they have to go back to the way they were before. That doesn't happen. What probably happens is one set of neurons picks up the task for one situation and another set of neurons or a neural circuit picks up the task for another situation. Here's a picture of this data, of this study. So I do a pre-control group, right? So I look and I just say, okay, tell me, draw me a grid as to where you think the sounds are coming from. And people are pretty good at it. They can go anywhere from 0 degrees to minus 30 degrees to positive 30 degrees, left and right, as well as left and right. And they can tell me with fairly good accuracy where sounds are coming from. If I were to put this mold inside the ear to eliminate this ability to judge elevation, on the first day that I put it in, look at this. I can tell if it's coming from the azimuth, where it's coming from, but I completely lose the ability to tell elevation. However, after a few days, after 19 days, the ability more or less comes back. It's almost as good as the control group. And then if I pop the mold out and then have you do it again, you're able to do it. It works really well. And what this suggests to us here, this difference here between the fact that my bent up pinna has adapted, and then if I go back to my regular old pinna, the fact that I don't have to, there's not an adjustment period here, tells me that there's probably two separate sets of neural circuits mediating this interaction here. Auditory nerve fibers, once they leave the cochlea, they synapse in a bunch of structures that are located in your pons and medulla and midbrain. One of the first stops is the cochlear nucleus. They also synapse in a part of your brain called the superior olivary nucleus, and it's called olivary because to the old anatomists back in the day, it looked like a little olive. And this is in the brain stem. There's also higher up in the midbrain the inferior colliculus. And we think the inferior colliculus has something to do with, well, in other critters, like kitty cats, for example, the inferior colliculus is responsible for regulating the direction of the pointing of the ears. But we can't move our ears, so the inferior colliculus helps us to judge location. And then, like all other sensory information, the sound then goes into the thalamus, specifically the medial geniculate nucleus of the thalamus. And then from the thalamus, it goes up into the auditory receiving area, the A1 in the temporal lobe, to begin the process of interpreting the message and the meaning of the sounds that you're listening to. And here's a picture of these areas. So here's your ear, the ear canal, the cochlea, and then the fibers from the cochlea, synapse here in the cochlear nucleus, the superior olivary nucleus, the inferior colliculus, and then in the thalamus and the medial geniculate MGN, the medial geniculate nucleus, and then from there it goes into the auditory centers of the cortex. Once the information goes into the cortex, it's processed in a hierarchical fashion. Namely, it goes through the processing, like in the visual system, the processing goes through a series of layers. Okay, a hierarchical layer. So the neural signals go to the core, then the belt, and then the parabelt area of the cortex. Very simple sounds, like a simple tone, cause activation in the core area. But more complex sounds, like music, for example, are going to activate more complex areas in the belt and in the parabelt area. So the more complex thing you're listening to, the more activation you have in deeper and deeper layers in your cortex. So right here we have the core area of the auditory cortex, the A1 area, the core area, and this is for simple sounds. And then as sounds get more and more complex, they activate the parabelt area and the belt area, and then the parabelt area of the cortex. This is not a human brain. This is actually a monkey brain, primate brain, but we have the same areas in our brain.